Here's a fun problem. Let's find the integral of sine theta over sine theta plus cos theta, and also the integral of cos theta over the same denominator. For now, let's ignore the fact that these two integrals look suspiciously similar, and let's just focus on the first one. There are many ways to solve this integral, but here's what we'll do. Let's factor sine theta from the denominator. We'll simplify things a bit, and we get 1 over 1 plus cotangent theta. Now, let's make the substitution u equal cotangent theta. Then du will be minus cosecant squared theta d theta. Rearranging gives us that d theta is minus sine squared theta du. Let's substitute that in. We need to write sine squared theta in terms of u. We'll draw a substitution triangle. Since u is cotangent theta, u is the adjacent side to the angle theta, and 1 is the opposite side. The hypotenuse will be square root of 1 plus u squared. Hence, sine theta is 1 over square root 1 plus u squared. We'll plug that in for sine theta. Next, let's use partial fraction decomposition to split the fraction to a linear and a quadratic term. Let's set up our unknowns and multiply by the common denominator. Now, group the terms by the powers of u. Comparing coefficients gives us the following three equations for our three unknowns. If we solve the system, we'll find the following solution. Now, let's split up the integral into three parts. The first integral is just natural log of 1 plus u. The second integral is also log, but with an extra coefficient of 1/2 because we reverse chain rule. We recognize the last integral as arctan. And don't forget the constant of integration. Now we're almost done. We need to unsubstitute now. First, we'll rewrite arctangent u in terms of theta. In our substitution triangle, the last angle is pi over 2 minus theta. So tangent of that angle is u over 1. Hence, arctan u is pi over 2 minus theta. For the rest, we'll plug in cotangent theta for u. We're done, but let's simplify further. We'll factor minus 1/2 from the first two terms and expand the last term. We'll rewrite 1/2 log as log of square root, and we'll collect the constants together. Now, we'll use the identity 1 plus cotangent squared equals cosecant squared. Now, rewrite minus log of cosecant as log of sine, and collect the logs together. And that's our final answer. Nice, that wasn't too bad, but we'll need to do the second integral. What a drag. If only there was a better way. A way where we could solve both integrals simultaneously. Alright, now that we've seen how long it takes normally, we can better appreciate the system of integrals trick. Let's denote the integrals by I1 and I2. Then consider the equations I1 plus I2 and I1 minus I2. If we simplify the first equation, this actually just ends up being the integral of 1 d theta. Pretty convenient. And if we simplify the second equation, this is the integral of sine theta minus cos theta over sine theta plus cos theta. Now, we can make the substitution u equal sine theta plus cos theta. Du will be cosine theta minus sine theta, which we can multiply by a negative to get the numerator. Substituting, the integral is just minus du over u, which is minus log u. Pretty quickly, we've solved the integrals in both equations. Now here's the cool part. If we add the equations, on the left-hand side, we get 2i1. If we rearrange the terms, collect the constants, and divide by 2, suddenly we have our original answer for i1. We can also solve for i2 just by plugging in our solution for i1. We've solved both integrals by doing 2 easy integrals rather than 2 long integrals. What a bargain! Can you think of other examples to apply this to?